Okay, in order to push and extend our understanding and comprehension of terms and concepts that we're learning, we're adding essay questions to the quizzes because I always ask those on the exam, and it's obvious from the midterm exam that we need more practice. So we'll begin practicing on the quizzes. So everything you need to answer these 5 questions can be found in the videos of the introductory video, the help video on the assignment, the help video on the lab. But let's concentrate it here and just one by one go through and answer these questions. Before we start, understand that there's a distinction. There are 2 kinds of things referred to here: terms, concepts, and relationships. So a term or a concept, those are pretty much interchangeable. A term is a word that refers to some physical concept, so I can pretty much use those interchangeably. And when we're talking about terms and concepts, there's always a definition associated with them. And the definition is more often than not in physics and in other sciences, engineering, an equation. And when defining a term and concept, it's always useful, really required, to mention the units, because we're talking about physical concepts, and those units are essential in understanding any term or concept. And then if we're going to explain it, we always use words, equations, diagrams, and examples. The other item or situation are relationships. So this week, an important relationship is the Impulse-Momentum theorem. Right? And it's the relationship between 2 concepts. It's the relationship between impulse and momentum, and that relationship is that impulse is equal to the change in momentum. So that relationship is, in fact, an equation. But to explain that equation to someone, you want to use words, diagrams, and examples. Now, since we're in remote learning, it's pretty difficult to draw diagrams on Moodle, but you can often refer to diagrams in the quiz itself. So you'll have diagrams of 2 carts colliding, equal or unequal masses, and so you can refer to those diagrams or use those as examples to illustrate either a term concept or a relationship. Okay, so with that in mind, let's go and answer the 5 questions. So question 1 is maybe the easiest, because it's just asking to define the terms, not explain. It could ask you to define and explain the terms impulse and momentum. So the first thing I'm going to look for is the equation of each term. That is the definition. And when I look at the equation, I want to see that it's a vector equation. They're both vectors. If you remember the symbol J or not, it's okay, or you write IMP, that's not a big deal, but they are vector equations. And if you just wrote this, I would probably give you credit, but identifying J as the conventional symbol and identifying the fact that that product of force times time, this only works if the force is constant. And if the force is not constant, then you have to use the average force. But the most general definition of impulse is the integral of the force time dt, f dot dt, and this is a vector. And I'm not going to go into that now, but if the force is varying, what you do is you should understand the integral. By now you've encountered it, or you will encounter it. The integral is an infinite summation. So if the force is varying, you multiply the force times a very short period of time, and then you do it again and again, and you add up all those contributions. And when you study calculus, you'll see that's the area under the force versus time curve. Okay, there's a lot more to say about that. And so, yes, this is probably adequate, but this is a much more complete definition of the term impulse. And notice I mentioned the units. So this is the kind of, you might just say, oh, impulse is the force times the time, and use those words. That's not very good. Absolutely, I need to see the equation, and the equation needs to show that you understand it's a vector equation. And you should include the units. And notice that the natural units of impulse are newtons times seconds. You might point out that that is in fact equal to kilogram meters per second, which are the units of momentum. And of course the definition of momentum is fairly easy. The symbol P is equal to the mass times the velocity. Momentum is a vector because velocity is a vector, and these are the units. And so you write down this and you put down the words, right? The words that I just said. And that would be a good, full, complete answer to question 1. All right. Try question 2 on your own and then see what I say, rather than just listen to me. And you do want to prepare these questions for the quiz on momentum and impulse. Okay, question 2, start with the equation and then explain it. So the key word to use here is the impulse momentum theorem, and I give you that, is the relationship between impulse and momentum. And it says that the impulse will be the impulse on any object or system of objects. It works for individual objects or systems of objects. The impulse on any object will be equal to its change in momentum. And it's a relationship between two concepts, impulse and momentum, but it's equal to the change in momentum. And you can, if you're really on your game, you'll point out that it comes from Newton's second law, which says that the net force acting on any object is the mass times the acceleration. And if we write out the acceleration as delta v delta t, then we get this relationship. And the units, you can point out that the units of impulse are Newton seconds, but that is equivalent to kilogram meters per second. And finally, going one step further, the impulse momentum theorem shows that if the net force acting on, usually it's a system of objects, like two carts are isolated on a frictionless track. So if the net force acting on a system of objects is 0, then the change in momentum would be 0. And that leads to the relationship, which we call the law of conservation of momentum, which is the next question. So the statement of the law of conservation of momentum is pretty easy, just P initial equals P final. And it's good to point out, in the collision between two objects, this is what it looks like. Just so that you understand, like, how do you do P initial? Well, you take the momentum of all objects in the system at the beginning, and you set it equal to the momentum of all the objects of the system at the end. But when does this law hold true? We turn to the impulse momentum theorem. So it's good to point out the impulse momentum theorem says that the momentum of something changes only if a force acts. So if we have a system in a collision of two objects, the momentum of each object is going to change because there's a force on it. But the system as a whole, if it's on a frictionless flat surface, has no net force on it. And so in the case where the force acting on a system of objects is zero, there'll be no momentum change to that system. And so what is that? That's our isolated system. Isolated means it's isolated from external forces. And so that's an important idea to get. The momentum of each of these is going to change, but what we've seen is that this is going to undergo a negative change in momentum, which is equal and opposite to the positive change. So whatever the initial momentum is, it will be equal to the final momentum because we can consider this an isolated system. So I'm skipping ahead to question 5 because that should have been question 4. So the quick and easy distinction between elastic and inelastic collision is elastic means energy is conserved. Momentum and energy are both conserved. So when two things collide with a spring between them, the energy is stored in the spring, and when the spring compresses and then decompresses and they go back, that energy is all returned. Inelastic means energy is not conserved. And if you have Velcro or some sticky silly putty or something like that, then the energy will be absorbed by the material. In most collisions, materials are deformed. It takes energy to bend the frame of a car, and so energy goes there and is lost. Most collisions are inelastic, and even when we do in lab, we do the spring carts, we see that oftentimes, even with the springs aren't ideal, perfect springs that return all the energy. So even in the case of a spring collision, oftentimes 20 to 25% of the energy is lost. Okay? So the simple idea is elastic collisions means there's a bouncing elastic collision and the energy is returned. If it's perfectly elastic, all the energy is returned. Inelastic, sometimes all the kinetic energy is lost, like two carts colliding and stopping, or sometimes partially lost. Okay, let's answer the last question, and we're done. So it's good to learn to relate and integrate what we're learning and what we have learned. And you'll notice that there's a lot of parallel between impulse, which we've talked a lot about. It's the integral of f dt. In the simple case, it's the average force acting over the time over which it acts. This is the simple way of thinking about it. In contrast or comparison, work is the integral of the force times the distance. Well, in fact, the force times the distance times the angle between those two vectors, right? It's an integral dot product. Okay, that's actually Calc 3, but you might as well get used to it. You're going to learn it. In the simple case, it's a force times the distance times the cosine of the angle between them, because it's only the component of the force in the direction of the displacement that causes the work to be done. Right? So force times the time, impulse does what? It changes the momentum of the system. It changes its velocity. Whereas work does what? It changes the kinetic energy of the system, or in some cases the potential, but to think of it in a simple case, if we do work on something, we change its kinetic energy, and that's the velocity squared. So there's, without going into any more detail, there's some important differences here. Let me just show you just one quick example and we'll be done. So here's the cannon example. We have a cannonball inside and the gunpowder explodes, and the cannonball goes off this way with an equal and opposite momentum, right? Because we start with 0. Momentum has to be conserved if we consider this isolated system. And the change in momentum of the cannonball and the change in momentum of the cannon are equal and opposite, and they cancel each other. Because the force acting on the ball and the force acting on the cannon is always the same, and the length of time that the force is acting on the cannon and the cannonball is the same, so the change in momentum is the same. Whereas when we come to energy, notice that the force is going to be the same, but the cannonball, when the force acts, the cannonball goes very far, whereas the cannon doesn't go very far. The cannonball goes the whole length of the barrel and then comes out, whereas the cannon just recoils a short distance. So although the force is the same, the distance is not the same. And so what happens is the kinetic energy of the cannonball ends up being much bigger than the kinetic energy of the cannon. So although the momentums are equal, the kinetic energy isn't equal. And from a conservation of energy point of view, it's the potential energy stored in the gunpowder has been transferred to the cannon and the cannonball. But what happens is the cannonball ends up getting as much as 10 to 100 times more energy than the cannon, in contrast to the momentum, which are equal. Okay, we're done.